Look at a modern, open concept floor plan. The sightlines are clean, air flows freely, and massive atriums connect multiple floors into a unified environment. In a fire event, those architectural choices become severe liabilities. Without physical barriers, smoke rapidly ascends open escalator shafts, reaching upper floors in seconds. This introduces a serious paradox in modern structural design. Features engineered to maximize human comfort and spatial efficiency, like continuous HVAC networks and vertical lift shafts, act as the primary pathways that accelerate a hazard. Fire compliance is a foundational engineering constraint that dictates the building's geometry from the very beginning, rather than a secondary feature added to a finished design. Safety emerges from engineering the structure to actively manipulate the fire's path. By delaying the spread through specific geometric constraints, the building buys a calculated window of time for survival. In India, the legal and engineering framework governing these structural constraints is the National Building Code, 2016, Part 4. The code recognizes that absolute safety from fire is practically unattainable. Its objective is pragmatic: provide a mathematical framework to maximize the time available for occupant egress while ensuring the core structure remains stable. Achieving this requires an approach that locks material science, spatial geometry, and mechanical systems into a single interlocking strategy. True compliance begins before the first foundation is poured. The code acts as an invisible blueprint, running parallel to the architect's vision. The first step of compliance is determining a building's occupancy classification. The code separates structures into groups A through J, ranging from residential towers to hazardous industrial facilities. That classification directly dictates the required type of construction for the project, categorized from Type 1 down to Type 4. The core metric that binds these two factors together is the fire resistance rating. This table outlines exactly how that metric is applied, mapping the fire resistance requirements for every structural element in the building. This rating measures a material's load-bearing capacity and thermal insulation against specific minutes of intense fire exposure. For example, an exterior structural column in a Type 1 construction must withstand a 240-minute burn without failing. A Type 4 construction carries significantly lower time requirements. This rigid mathematical matrix ensures the building's skeleton outlasts the calculated evacuation timeline for the specific occupants inside. Once the structural timeline is secured, the interior is divided into fire compartments, a strategy of sealing a fire exclusively to its zone of origin. The flue effect is the greatest threat to this strategy. Heat and smoke naturally seek out vertical shafts and concealed spaces, creating a vacuum that pulls the hazard upward through the building. Plumbing and electrical ducts are permanently sealed with intumescent fire-stopping materials, but architectural features like escalators present an unclosable vulnerability. This technical diagram from the code shows the mechanical requirement for mitigating that open escalator. The opening is surrounded by a draft barrier extending 450 to 600 millimeters down from the ceiling. This barrier is paired with high-velocity sprinklers, designed to generate a water curtain that physically beats back the smoke. Similarly, motorized fire dampers are required inside the ventilation network. When a sensor detects heat, these steel plates automatically seal off HVAC ducts where they cross fire-rated walls. Structural walls require these interlocking active systems to defend their intentional penetrations. With the fire contained, the code dictates the written spatial geometry of the means of egress. This schematic defines an approved escape route, breaking it down into 3 distinct sequential zones. First is the exit access, the standard corridor routing occupants away from the hazard. The second zone is the exit. This is a continuously fire-rated enclosed structural box, typically a pressurized staircase, engineered to completely isolate occupants from the hazard on the floor. The final zone is the exit discharge, which provides a clear, unobstructed path from the bottom of the staircase directly to a public street. An egress route functions as a sequentially fortified channel. It is a rigid spatial machine designed to shield human psychology and physiology from the environmental hazards of the fire. A high-rise fire presents a massive logistical nightmare. Occupants must evacuate downward, while emergency responders push upward with heavy equipment. To prevent a bottleneck, the code mandates a dedicated firefighting shaft. It relies on passive structural defenses, isolating the lobby with 120-minute fire-resistant walls. Inside that protected box, the fireman's lift remains operational, alongside a wet riser equipped with a high-pressure hose reel. This layout creates a pressurized staging area on the burning floor, allowing firefighters to assemble gear and charge their hoses before entering the hazard zone. The building itself is utilized as a tactical asset, providing responders with a fortified beachhead to launch their attack. Active defenses, including dampers, water pumps, and pressurization fans, depend entirely on electrical power to function. During a major fire, primary grid power is typically lost or intentionally severed. A redundant emergency generator system must automatically take over the load, instantly illuminating the egress routes and forcing water up the risers. This logic is routed through the fire command center on the ground floor, which monitors alarm inputs and directs backup power. Without this electrical nervous system, the massive concrete compartments and heavy steel doors of a building are effectively blind. The methodology of Part 4 relies on 3 interlocking layers: passive structural matrices, rigid egress geometries, and the active mechanical defenses that guard the gaps. These systems are designed to overlap. If an active sprinkler system fails, the structural compartmentalization preserves the evacuation timeline. True compliance with NBC 2016 Part 4 transforms a building from a static piece of architecture into a dynamic, heavily armored life safety machine.